there. So we're back. Let's see. I believe that this is Tuesday, April 28th. Let me go check. Yeah, so this is the video for Tuesday, April 28th. We have one more problem to finish in 6-6, and then we're going to go do 6-7 and 6-8. Quiz 4, which was given to you on last Thursday, is due today. The deadline is your class time start. So depending upon when your class starts, that's your deadline. But that was also, you were told that in the email that came last Thursday when the quiz was handed out. And then the only other announcement here is that test 4 is coming up. It's on chapters 6 and 7. I know you're like, wait, we haven't even started chapter 7 yet, and it's already around the corner. Chapter 7 we're going to do on Thursday. We only do 7-2, 7-3, and 7-4, and they're all sort of a little interrelated. And so we will be doing that in Thursday's lecture, in Thursday's class. So just an announcement that's coming. Test 5 on your syllabus, I think we discussed this once before. Now we'll discuss it more seriously. That will not be a test. That test 5 will be turned into a quiz that will be handed out to you as a take-home, just like normal. It will be worth 10 points, like a normal quiz. And once we get through test 4, it'll come out. It'll actually come out early so you can be working on it. And I'll give you that information when we get there. So there's my announcements. We're ready to go ahead and continue. We have one more problem to do in 6-6. So let's go get that done, and then we'll move on. So this is 6-6. Oh, this is 6-6 continued with our last problem. And this last problem is a favorite of mine, so just as a comment, because it really makes you work to get the answer and understand all the properties. So that's what it says. They've asked me to solve it. And so when I look to see what kind of an equation it is that they want me to solve, the first thing I notice is that the unknown is in the exponent, which means it's exponential. So that means I'm going to try and create same bases. And if I can't create same bases, then I will take the idea of introducing a log on both sides. So when I look at these bases, this is a base of 2, which isn't going to change. So can I turn 5 into a base of 2? And you tell me no way. So I can't create same bases. So since I can't create same bases, the next resort is to introduce a log in front of each term on each side. Since it's just a base to a power and a base to a power, I'm going to introduce a log. You can introduce ln if you want. I usually say that if there's an e in the problem, because then that makes life nicer, and we'll get some of those in the last section in this chapter. But for this, I'm just going to do log base 10 and use that key in my calculator. So I'm going to take log of 2 to the x plus 1, and notice I'm not putting a base in because I'm saying it's base 10, and I'm going to put a log over here, also base 10 of 5 to the 1 minus 2x. So again, you look at that and go, oh my gosh, it makes it look more complicated. And it does a little bit, but again, the idea here is by putting the log in front of these, I can use that property of logs that says if you have an argument to a power, the power can come out here as a multiplier. The thing that makes this a little more difficult is that this power has more than one term in it. So that means when it comes out as a multiplier, I'm going to put parentheses around it and understand that, so I've got x plus 1 times the log of just plain old 2, but understand that this is going to need to distribute because I've got a couple terms here. And over here on this side, the same idea is happening. This 1 minus 2x is more than one term. So I'm going to put parentheses around it, and it's going to now be multiplying with the log base 10 of 5. So it still looks more complicated. And it is in the sense that you actually have to do this multiplication now. Before it was just one term here, and so it was just whatever that term was times the log of 2, and life was a little bit easier. But now it's a little more complicated, and I need to actually distribute. And when I distribute, I get x times the log of 2 plus 1 times the log of 2, which is just the log of 2. So that's what the left side now says. The right side, when I do the same idea, I take 1 times the log of 5, I get log of 5. And then I take negative 2x times the log of 5, and I get minus 2x log of 5. So now what do I do? So now I've got logs all over the places, but the question is what kind of an equation is this actually? Where is the unknown? Remember, log of 2, that's just a constant. It's something that I would have to approximate if I want to get, because otherwise it's a little bit meaningless to me in terms of knowing what that constant is. Log of 5 is a constant. That log of 5 is a constant. That log of 2 is a constant. The unknown here is here and here. This is linear. This is a linear equation, which means we're going to get all the x on one side, get all the constant on the other side. So that means, I like the idea that this one's positive here and over here it's negative, so I'm going to actually add 2x log of 5 to both sides. Add 2x log of 5, which means if I'm getting all the x on the left, I'm going to get rid of this log of 2, so minus log of 2 minus log of 2 to both sides. So what do I have going on here? This x log of 2, and then I'm going to add a 2x log of 5. These are not like terms. The fact is that even though the x and the 2x are alike, this constant, I don't know what it is, and as a result I can't combine these two, so I'm just going to string it out. X log of 2 plus 2x log of 5 is equal to, these log of 2's go away, that was the whole point of that. Over here, the 2x log of 5's go away, and I'm left with log of 5 minus log of 2. So this is now what I have going on. And again, I usually don't do this step. I just take terms and move them on either side, and that's fine. Notice I didn't move this one. I took this guy and brought him over here, which made him positive. I didn't move the log of 5. I took this guy over there and made it negative, and you can always do that as well. So here's what I have. I'm trying to solve for x. So trying to solve this for x, and I can't combine these two. How do I solve it for x then? Because to solve for x, I have to have x multiplying with something so that I can then divide it away. Well, the fact is in order to have x multiplying with something in this expression, what is it that I need to do to this expression? And I see people saying it. You're saying, factor it, factor it. So that's what I'm going to do. I'm going to factor it. So I'm going to take the x out. So I factor out the x because they have the x in common. And I'll be left with log of 2 plus 2 log of 5. Nothing but the constant part. Equals log of 5 minus log of 2. So now how do I solve for x? X is multiplying with something, so I will divide by that something. So I'll divide this side by log 2 plus 2 log of 5, and I don't really need the parentheses here. And then I'll divide this side, entire side, by log of 2 plus 2 log of 5. So that cancels, and I'm left with x is equal to log of 5 minus log of 2 all over log of 2 plus 2 times the log of 5. Can I simplify that? So I know it's tempting. You want to like slash those logs of 2's and maybe those logs of 5's. And if you can't factor something out of both terms that then will cancel, then you can't cancel. If it's not a factor, you can't cancel it. There's no way I can factor anything out of these two. There's no GCF here that I can factor out. So I cannot cancel anything. That's simplified in terms of trying to simplify a fraction. So this is my exact answer. It is meaningless because you know, it's a constant of some kind, but I don't know what it is. So I'm going to go put it in my calculator to get the approximate answer. So my approximate answer. So I'm going to go grab my calculator here. Well, actually, I'll do it without the calculator since I've got it down here already. So the approximate answer is, I got to put this into my calculator very carefully. So in my calculator, and we're going to round it to 3 decimal places. It looks like what I want it to be. So how do I put this in my calculator? So you go, okay, you hit the LOG key, and a parenthesis comes up, and you type in the 5, and you remember to close the parenthesis. Good for you. And then you write minus, type in a minus, then you hit the log key again, and a parenthesis comes up. You put a 2 in there, and you remember to close the parenthesis. You're getting better at that now, right? And then you hit the divide by key. I've already done something wrong. Because here's the deal. The minute I hit that divide by key, order of operations, my calculator is going to take this guy right here and divide it by whatever I put there. So I have an issue here. That's not what I want to have happen. I want this to be figured out first, get an answer, and then divide it by this being figured out. So what am I going to need to do here? I'm going to need to put parentheses around the numerator and then around the denominator. So then my denominator, I'm going to put a parenthesis. I'm going to type log. A parenthesis comes up for the argument. I close it. Plus 2. You don't even need to put a time sign here. If you put the 2 and then hit the log key, it knows that you want to multiply. 2 log, parenthesis comes up for the 5. Close it, and then close the denominator. So in other words, this is saying, figure out the numerator, figure out the denominator, and then divide the 2. And if you enter it that way, and you round it to 3 decimal places, it comes out to be 0.234. So this is my approximate answer. And that's how you want to put it into your calculator. Now, if you want to get fancy, see this guy right here? So let's get fancy. I'll even write it down. Let's get fancy. I'm going a little crazy here, I guess. So I'm going to get fancy. Can you adjust this a little bit for me? In other words, use the properties of logs. If you want to, it might make it easier to put into your calculator. This x is equal to, do you have to do this? No, this is fine. And then put it into your calculator carefully to get the approximate answer. But think about this. What is the log of 5 minus the log of 2? You've got subtraction of 2 logs. That came from a single log, if you condense it, log base 10 of what? 5 divided by 2, right? Okay. The denominator, I have to adjust this a little bit. Okay, so this is log of 2, so I'll take a couple steps here, plus log of, so in other words, I can't put these together until I get rid of this 2 here, and that 2 comes over here as a power. So what would my argument for my second log be? It would be 25, right? 5 squared. Okay, one more shot here. Log of, you want to even make this easier, you could just divide that and do 2.5 since it comes out evenly, but otherwise, you know, the argument here is 5 halves, so I'm going to leave it alone. This one now becomes single log. These are added, so what are you going to do with these 2? Multiply them. This is easier to put in the calculator. Easier in the calculator. But if you make a mistake getting there, then you've messed yourself up anyway. But so you can always do that if you want. And do you have to do that? No. If you want to leave it in this form, that's fine, as long as it's simplified, which it was. And then you can just very carefully get it into the calculator. Or you can get fancy and rewrite it so it's easier to put into the calculator. So that finishes 6.6. We're ready to move on to 6.7. Let me get rid of this. So 6-7 is all about these things called financial models, and basically it's interest formulas. So we talked a long time ago about simple interest, which was principal times rate times time is equal to simple interest, where you're just taking one shot at however much money you're putting in there, and you're doing an interest rate on it and adding some extra money into your account. A lot of accounts don't do simple interest, or at least I think still, most of them do compound interest, or even what's called continuous compounding. They all have formulas to figure them out, and that's what this section is about, is just sort of using these formulas and understanding where the pieces fit in together. So I wrote down the compound interest formula. So when you're compounding interest instead of simple interest, when you're compounding interest, the formula that you use looks like this. A is equal to P times the quantity 1 plus R over N, all to the power of NT, where, so off to the side I wrote, R is the interest rate converted into a decimal. So in other words, it's the percent converted to a decimal. T, that T right there, is time in years. So this formula is very specific. The time has to be represented in years. So if they tell you 6 months, then you need to write 1/2 for the years. P is the principal or the present value. In other words, how much money you have right now. N is the number of times, it's there twice, the number of times it's compounded in a year. So in other words, if the bank or whoever it is tells you that they're going to compound yearly, that means you're only going to get that interest applied 1 time a year. If they tell you they're going to compound it quarterly, that means that you're going to get it compound 4 times a year. If they tell you they're going to compound it monthly, that means you're going to get it compounded 12 times a year, so N would be 12. If they tell you you're going to get it compounded daily, then you're going to get it compounded 365 times a year, so N would be 365. So N depends upon how many times they tell you they're going to be applying the interest to your amount in the bank. And A is the future value. In other words, how much money you'll have after a period of time. So again, P is how much money you have right now when time is equal to 0, right at the beginning. And A is how much money that you'll have after time is more than 0, like after 1 year or 2 years or whatever the time period is that they tell you. Oftentimes, we call this guy, a lot of books use FV for future value instead of the A. So you'll notice in my description to the right, I said A is the future value. And oftentimes, instead of writing P, sometimes books will write PV for present value. I'm trying to stick with the way this book does it, which they use an A and a P. The next formula is the continuous compounding. And the difference with this guy, and you'll notice these are in here because they are all exponential equations. They have unknowns in the exponents. So that's why they're in this particular chapter and section. So continuous compounding, you'll notice that formula says A is equal to PE to the RT. Some of you, if you've taken any kind of business classes, you might have seen that before, where they say it's PERT. Notice the E. What's E again? Is E a variable? It's a number, right? So this is a number that we approximate with 2.72 or 2.718, depending upon how we want to approximate. It's an irrational number. So the variables there are the A, the P, the R, and the T, not the E. The E is a constant. So this guy, well, for continuous compounding, notice same P, present value, how much you have right now, time equal to 0. A is the future value, how much you'll have after however many years have passed. E is a constant. R is the same R, it's the interest rate expressed as a decimal. T is the same time, it's time expressed in years. The only thing that's not there is the N, right? How many times it's being compounded a year. That's because continuous compounding means that it's going to compound as quickly as the computer can do it. So every nanosecond or whatever, it's adding money into your account and compounding with the interest rate. So it's a continuous compounding. So it acts more in an e to a power type of way in terms of figuring that out for how much money you have. With both of these, because neither one of them are simple interest, where you just have your amount in your bank and they take an interest rate of it and they add that money onto it and you're done. This is different. Both of these are different in the sense that you're actually computing interest on interest. So in other words, if I get it compounded, let's say monthly, so every month I have an original amount in the bank, they figure out the interest on it at the interest rate that they've given me, they add that to my amount in the bank, and then the next month they use that same interest rate that they gave me, but now they're applying it to my original amount plus the interest they gave me the month in the previous month. And so we're doing interest on top of interest. And so of course compounding interest or continuously compounding are better ways to go if you can manage to do it. In fact, continuous compounding is the best because you're constantly readjusting and adding interest onto interest. So the next set of formulas that are called the effective rate of interest, that's what that has to do with. The effective rate of interest, which we call the R sub E. So that R sub E is just a fancy way to say the words effective rate of interest of an investment earning an annual interest rate, so a percentage, compounding n times per year, or continuous compounding, two different formulas. The effective interest, which is the little symbol R sub E, for compounding n times per year is the formula 1 plus R over n to the nth minus 1. That's what I don't have memorized. Effective interest rate, what does that mean? It means that effectively, even though they've told you, let's say your interest rate is 3%, because they're adding interest because of the way they're compounding it, you're actually getting a better interest rate than 3%. And this is how you figure it out. What is the effective interest rate? It's going to be a little bit more than 3% because they're adding interest onto interest earnings. So that's if it's compounded n amount of times. Notice there's n's in that one. And if it's continuously compounded, then the effective interest rate is equal to the e to the r minus 1. So this is if it's compounded n times, and this is if it is compounded continuously. So I have those formulas down there, I have them split out. Now we just have 6 problems to do and see if we know which formula to use and how to follow it. So this first example, so I'm hoping you won't find this section too terribly difficult, says how much money will Joe have if he invests $100 at 4% compounded quarterly for 2 years. So I would make the suggestion to go ahead and label for me, in other words, take the time to tell me what's the interest rate, what's the time, do you know the P, do you know the N, do you know the A in these problems, and then decide which formula you should be using. So in this problem, how much money will Joe have if he invests $100 at 4%? So the $100 is what? That's how much money he has right now, present value. That's this guy right here. P is 100. 4%, that's my interest rate, right? But instead of writing 4% there, I'm going to write it as a decimal, which is 0.04. Compounded quarterly. So they're telling me how many times a year it is being compounded. If it's compounded quarterly, then n is going to be 4. Let's see. And it's being compounded quarterly for 2 years. So time is in years 2. So what do I not know? Right here. This is what I don't know, the A, the future value. So which formula am I going to use? It's compounded 4 times a year, so not the continuous compound, but the compounded interest, this guy right here. And I don't know the A, so that's kind of nice. So I write A is equal to P, which is 100, multiplying with 1 plus R, which is 0.04, over N, which is 4, all to the power of N, which is 4, multiplying with T, which is 2. So there's my formula right there. A equals 100 times 1 plus 0.04 over 4, all to the power of 4 times 2. I just need to put that into my calculator because I have everything filled in. Is this guy I don't know? So very carefully, I put this into my calculator. And here's where issues happen. So let me comment on this a little bit. If you want to do this in pieces, that's fine, but don't take the pieces and write down their answers from your calculator where you've rounded or truncated them, where you've cut off half of the numbers. And even your screen on your calculator cuts off numbers because it's only so long and can only hold so many, display so many numbers. The fact is the actual answer is in here in the programming. Do not round in the middle of a problem. So don't figure a piece out and write down. So let's say this piece gave you 0.235691043. It keeps going, but that's as much as you have. And then you go, oh, well, I'll just round that. I'll make this a 4. So I'll write 0.24, and I'll use that and do the rest of the problem. Do not do that. You're rounding too soon. The rounding needs to be done at the very end, not in the middle of a calculation. You can get into huge trouble if you round in the middle of a calculation, particularly if you're talking about really small or really large numbers. Your answer will be quite a bit off what it needs to be or what it actually is. So when you do this, you need to either put it all in one shot, or if you do it in pieces, then you need to keep that in here and keep going with it. So first, in one shot, if I put this in my calculator in one shot, how am I going to type it in? I'm going to type in 100. I'm going to put in a parenthesis. I'm going to write 1 plus 0.04 divided by 4, and I'm going to close that parenthesis. But now I'm going to think a little bit about this and make sure that this is doing what I want it to do. Order of operations, it will do the 0.04 divided by 4 first, and then it'll add 1, and that's exactly what I want to have happen. And then to the power of, so I put my caret, and then you type 4, and you hit the times, and you hit a 2. And now you're in trouble, and here's why. Again, order of operations. It's going to do this, and then it's going to do this, because you got parentheses there. And then it sees the caret, so now it wants to do powers, and the issue here is that what power is it going to take this to? It's only going to take it to the power of 4 because you haven't told it to take the power to the power of whatever 4 times 2 is. So it's only going to take it to the power of 4, and now you have an issue. It'll take this to the power of 4, and then it'll multiply that answer times 100, and then it'll take that answer times 2. You don't want the answer times 2. That 2 is part of the power. So to show it that that's what you want it to do, you need to put parentheses around that. Otherwise, it's not going to do what you're expecting it to do. So all in one shot, that's how I need to enter it. Clearly, if you can do that in your head and just put a caret and an 8 there, that's not going to be an issue. But sometimes this is hard to compute separately, and so just put it in parentheses and tell it to take the whole thing as the exponent. Again, if you pick it apart and do it in pieces, if you do this piece first, you'll get an answer. Don't round it. Just leave it on your screen and then say caret, and actually, so if you do it a piece at a time and you take that piece and get an answer, and then you want it to take it to the power of something, then what will happen is that it'll come up like this, answer, power, and then you take 4 times 2 and put it in parentheses. So you can keep going. Do not round. Do not round in the middle of a problem. So when I did this one, and I put it all in at one time, and sometimes I do break it up into pieces. Sometimes I do it both ways just to double check. But when I did this one, what spit out here is that A is equal to, and this is without any kind of rounding, this is what showed up on my screen, 108.2, can I read that? 2856706. It keeps going, but my screen didn't have any more room available. So this is what A is, and they want, what is A representing? It's representing future value. So this is money, which means that my future value is going to be approximately, I'm going to put in a dollar sign, and since it's money, I'm going to round it appropriately for money, so I'm going to say $108.29 is approximately what that future value is going to be. So future value. So my Joe's $100, Joe, yeah, $100, 4% compounded quarterly for 2 years. After 2 years, he's going to have $108.29. Hardly worth it. So there's that first one, figuring out what formula to use and then getting it in your calculator properly. I guess I'm going to these. So number 2 says, how much money will Joe have if he invests $400, so he has a little more money now, at 7% compounded continuously for 3 years? So again, take the time to write down the R, the T, the P, the N, and the A. It's just useful to be able to do that so you know which things you're trying to figure out. So how much money will Joe have if he invests $400 at 7%? So right now, how much money does he have? $400. So his present value is 400. He's going to invest it at 7%. So the interest rate is, as a decimal, 0.07. Compounded continuously. Compounded continuously. So the N, this is continuously, which means we're switching formulas for 3 years. So time is 3 in terms of years. Again, I don't know the A, the future value. So this is the guy I don't know, but the formula I'm using now, because I'm compounding continuously, is A equals PE to the RT. So P is 400, E to the R, which is 0.07, multiplying with T, which is 3. So A equals 400, E to the 0.07 times 3 is what I need to go figure out. So when I put that very carefully into my calculator, and again, how am I going to put this into my calculator? If I type, so in calculator, if I type 400, and then I hit the E, and what comes up, remember second ln, E comes up actually like that, waiting for you to put in a power. So what am I going to do here? So this is kind of nice, it prompts you. I'm going to put in 0.07 multiplying with 3. Just one big parenthesis around that to show this is the power that I want the E to be taken to, whatever the answer is to that. If you want to figure that out, that's fine. Don't round it though, okay? So, and when I do that in my calculator, what spits out was, let's see, 493.471,224, blah, blah, blah. I want you to write that down. So each time I want you to write down what your calculator spit out, and then you're going to round it to the appropriate thing. This is money again, this is future value. So the future value is approximately equal to $493, and if I round it to cents, 47 cents. So this is my future, or Joe's future value. That $400 is going to turn into $493 approximately and 47 cents after 3 years if he compounds continuously. So having a little more money to put in there and the continuous helped a little bit too. He's got a little more than he realized in the other problem. So number 3. Says that Joe needs to have $300 after 4 years at 3% compounded daily. How much should he invest now? So again, I'm going to think about my R, my T, my P, my N, my A, and my A. So what do we know here? It says Joe needs to have $300 after 4 years. So what's that $300? Is that how much money he has right now? Now that's how much he wants to have after 4 years. So 300 is the future value, so it's my A. After 4 years, so time is 4 in terms of years. Compounded 3%. 3% is the interest rate, so 0.03. Compounded daily, so this is my N is daily, which means how many times a year is that going to be? 365, because there's 365 days in a year. How much should he invest now? That's my present value, so that's what I don't know. So, which formula I'm using? I'm using the compound interest one, which says future value, which is A, which I happen to know, 300, is equal to my present value, which I don't know, multiplying with 1 plus R, which is 0.03 over N, which is 365. So 0.03 over 365, all to the power of N times T, which would be 365 multiplying with 4. So there's my formula. But now look at where the unknown is. The unknown here is, darn, I can't just calculate things. It's P is my unknown. So how do I solve this for P? Well, you could figure this out, but then you're going to be tempted to round it, and I don't want you to do that. To solve this for P algebraically, when you figure this out, what would you have to do with it to get this solved for P? You would have to divide by it, right? You'd have to divide 300 by it. So what I'm saying here is that if I take the 300 and I divide it by the answer to 1 plus 0.03 over 365, all raised to the power of 365 times 4, that will give me P. In other words, P is multiplying with that. So divide that side, you'll get P. Divide this side, and you'll get this crazy looking expression. This is what I need to put into my calculator. So in the calculator, how do I write this in my calculator? Very, very carefully. So let's see. You could do 300 and then divide by, and I need these parentheses regardless because of that power, so I'm going to put in a parenthesis. I'm going to write 1 plus 0.03 divided by 365. Close that parenthesis. I'm going to make sure, we've already talked about this though, is this doing what I want it to do? It's going to divide that and add the 1, so that's perfect. And then I want it to be to the power of, and I'm going to have to type 365 times 4 here, either that or figure out what 365 times 4 is. So that'll give me this properly to the power of this properly. But now the question is do I need an extra set of parentheses maybe here? And honestly, when in doubt, put them in. If you're not sure, it's not going to hurt to tell the calculator, hey, this is my denominator, this is my numerator. I don't really need them around the numerator, but I might need them around the denominator, and if I'm not completely sure, then I will put them in just to make sure. But if I think about order of operations, it does parentheses, PEMDAS, right? Parentheses first, then exponents, so it's going to take this answer to this power, and then multiplication and division from left to right, so it'll do my division. So this should be fine. Is there anything wrong with putting an extra set of parentheses in there? No. So when I put that in my calculator, it spit out that the present value is equal to 266.0774431. It keeps going. I just don't have any more room on my screen. So that means that my present value is approximately equal to, this is money, so I will round it to the appropriate money, $266.08. So what is this telling me? So this is my present value. In other words, this is how much money I need to have right now, or who is it, Joe again? This is how much money Joe needs to have right now to put into the bank so that he can realize $300 after 4 years. Wow. So again, understanding which formula, understanding my calculator a little bit. I will tell you, sometimes what I do with this is I do figure this out separately. And then there's a key in your calculator. So if you figure out the denominator, so let me see if I can do this real quick. So if I just figure out this, so alternatively, if I figure out 1 plus 0.03 over 365 to the power of 365 times 4, if I put that in my calculator, so I put a parenthesis, a 1 plus 0.03 divided by 365, close my parenthesis, to the power of, and then I put a parenthesis, 365 times 4, close that parenthesis, and I hit equal. My calculator says 1.127491292. It keeps going, but I don't have any more screen room. I don't know if I can get that. I don't know if this is working or not, or if you can zoom in. But clearly that's just the denominator. So what good does that do me? Because I have to take 300 and divide it by that. So don't clear this. Don't write down 1.13 and round it and then take 300 divided by that. What you want to do, just leave it, don't clear it. Now I want you to type in 300. So now type in 300 divided by, so do 300. So it looks like it goes away, but it hasn't. And then hit the divided by. And then say second, and then hit the second and the negative key, which has an A and S above it. That's answer. So I want you then to type second and then the negative key. And what you'll see 300 divided by answer. So again, I don't know if this is working or not, but that's what you'll see, which is basically in the calculator, it's taking 300 and dividing it by the answer that you got when you put this in, hit equal, and what spits out is 266.0774431, etc. So there are ways to use this calculator to our advantage. Unfortunately, I can't be there in class with you, but hopefully I'm explaining it reasonably well that you can play around and see if you can figure it out. So that's number 3. Let's go take a look at number 4 now, see what we can do with it. So number 4 says, what rate of interest compounded annually is required to triple an investment in 10 years? Okay, so let's see, we've got RTPNA. So what rate of interest? So we don't know the rate of interest. Okay. Compounded annually. So compounded annually means N is 1. So compounded annually is required to triple an investment, we'll come back to that, in 10 years. So time is 10 years. But I feel like there's too many unknowns here. We don't know, they're also saying, they're not telling us what the investment is, but what they're telling us is that whatever we're putting in, we want the future value to be tripled, right? So, I don't know what my present value is, so I'll just call it P. My future value needs to be triple the P, so 3P. So this is an important idea to understand what's going on here, because they didn't tell us how much money, and you're thinking, how can I have so many unknowns? I only have one formula, and that's true. But we're going to find that this will take care of itself in a second. So what formula am I going to use? I'm going to use the compound interest formula, which says future value, which is 3P, is equal to present value, which is P, multiplying with 1 plus the interest rate, which I don't know, over N, which is 1, all to the power of N, which is 1, times T, which is 10. 1 times 10. So this is what I have to figure out, but you still look at this and you go, wait, there's too many unknowns here. It's the interest rate I'm trying to figure out, but then I also have this P that I don't know. But the fact is, so I'm gonna do something that I tell you never to do. So I told you a little while ago, and it's still true. I'm not changing what I'm saying. You should never divide both sides of an equation by a variable, because when you do that, it means that you are assuming that variable cannot equal 0. And sometimes it can. Sometimes that is one of the answers. But in this practical application of this problem, if I divide both sides by p, because p is being multiplied by something here, p is also being multiplied by something here. If I divide both sides by p, I can get the p's to go away, and I only have one unknown. Why is it that I can do that in this problem? Again, the idea of not dividing by a variable is that you should never assume that the variable can't be equal to 0, because maybe it can. But in this practical problem, is p going to be 0? Well, p is my present value. And if I have $0 to invest, then why am I doing this problem? There's no point to it. So my domain, my understood domain in this problem is that p is not 0. So as a result, I can divide both sides by p. So I can divide by p because p is not going to be equal to 0. That's not part of my domain in this particular application. So I'm going to do that. I'm going to divide this side by p, and I'm going to divide this side by p. So this will just give me 3 equals, these p's cancel, and I just get 1 plus, let me simplify this, r over 1 is just r, and 1 times 10 is 10. So now it's in a more normal looking equation in the sense that I only have one unknown. Here I am going to break my rule here. Technically there are 10 answers to this problem, because if I were to multiply this out, I would ultimately have an r to the 10th. But the fact is, in this application, I want only real values for r. And the biggest real value for r would be from taking the 10th root of both sides, since this is positive over here. So I don't want to look at the imaginary answers, of which there would be quite a few. I only want to look at the real answer. So I am going to take the 10th root of both sides. Even though we don't have a property that says that we can do that, I'm going to take the 10th root of both sides. So this is the 10th root of 3 is equal to, this is the 10th root of all this to the 10th, so I would just get r plus 1, or 1 plus r. And I'll solve that for r, which means all I have to do is subtract 1 here. So r is equal to whatever the 10th root of 3 minus 1 is. So I'm going to go figure that out. So I put that into my calculator. And when I put the 10th root of 3, and so now you're thinking, how do I get the 10th root of 3 in this calculator, in this silly little calculator, because it only has a square root up there. So I'm going to tell you, you are going to go to, let's see if I can find it. So the square root key is over the x squared, but over the caret, you'll notice that there is a radical sign that looks like this. So over the caret, so in other words, I have to push second caret key. Oops, let me get rid of the answer. So second caret key. Oh, okay. So over the caret key, there is a symbol that looks like this, right? With a little X. It's so hard to see in my garage. What this is telling you is that you can put a 10th root, whatever root you want in there other than the square root. What you have to do first, though, is you have to put in the root first. So you need to type in, so in calculator, you need to go 10. Just type the number 10 in, so 10. And then you're going to go hit the second caret key to get this symbol to come up. So then you hit second and the caret. So in calculator 10, then do second caret, and what should come up is something that looks like this, 10, and then you'll see an X, and then you'll see a radical sign. So again, don't know if this is working or not, but I'll try to show you. It looks like this, and now you're going to type in what you want in there. So now you're going to type in a 3. I wonder if I should put parentheses there. So I don't use this very often. I do it a different way, but anyway, I'm going to actually type in a parenthesis and then a 3 and then a parenthesis because we need to subtract 1 from this answer. So it didn't bring up the parenthesis for me, so I'm going to type it in and end parenthesis. And then you're going to type minus 1. And then you put in minus 1. And what spits out is 0.116123. That looks really good. So what spits out here is r is equal to 0.116123174. It keeps going. This is an interest rate, okay, in its decimal form. So that means the interest rate written as a percentage and rounded, so let's round it to 3 decimal places. So first of all, as a percent, I move this 2 to the right and I get 11 points. And then I'm going to take it 3 decimal places, so 612%. So R is approximately equal to 11.612%. So that's the interest rate I would need to have compounded annually that would triple my investment, no matter what it is, within 10 years. I'd need 11.6% interest rate. I don't know if you can get those anymore. So that's what number 4 looks like. Just to comment, when I said I do these a different way, because I find this clunky in this calculator. This is, rewrite this. This is 3 to the what power? 1/10. So I find this easier to put in. So alternatively, I find it easier to type in like this, 3 to the power of 1 divided by 10, and then subtract 1. That's how I usually do those. I just like it better. Okay, so that was number 4. Let's go take a look at these last 2, and then we'll be ready to go to the last section. So these last 2 questions are actually trying to find the effective rate of interest. So that's those other last 2 formulas down there at the bottom of the formulas that were written at the top of the page. And it says, can you find the effective rate of interest for 6% compounded monthly? So we don't know the effective rate of interest. Do we know the R? I'm sorry. I'm not even going to do this. I'm just going to write down the formula here. So this is compounded monthly, which means that I'm going to be using the formula, the effective rate of interest is equal to 1 plus R over N, all to the nth power minus 1. So they're telling me that they want me to find the effective rate of interest. If the rate of interest, if the R is 6% and it's compounded monthly. So my effective rate of interest is going to be 1 plus R is 6%, so 0.06. Compounded monthly. So monthly means how many times a year? 12. Compounded monthly, all to the power of N, and then minus 1. So the only things I need here are the interest rate and how many times a year it's being compounded. So I'm using the first formula because they gave me an N. So when I put this into my calculator, again, how do I do that? So in calculator, I'm typing 1 plus 0.06 divided by 12. We decided that was okay. To the power of 12, oh, I don't even have to put this in parentheses because this is not anything I'm having to multiply. And then you just subtract 1. Order of operations will be respected here. It'll do this, the division, it'll add, it'll do the power, and then it'll take that answer and subtract 1, which is exactly what I wanted to do. So the effective rate of interest, when I put this in there, it spits out 0.0616778, blah, blah, blah. Again, the effective rate of interest is an interest rate, which means I want to write it as a percent. This is its decimal form, and it should be more than the 6% that we started with. Otherwise, I'm doing something wrong, because remember, we're putting interest on top of interest income. So we have a slightly higher actual effective rate of interest going on here. So in terms of a percent, I would move this 2 places to the right, and I would have 6.16. Let's take it 3 decimal places, so 6.16, and that would come up to an 8%. So my effective rate of interest there is approximately 6.168%. And this last one says, okay, find the effective rate of interest for 6% compounded continuously. So they didn't change anything other than it's not going to be compounded monthly anymore, it's going to be compounded continuously, which means I'm using a different formula because I don't have an n. So that first formula I needed the interest rate and the n, but this one all they give me was the interest rate because it's being compounded continuously. So the formula I'm using for the effective rate of interest this time is going to be the e to the r and then minus a 1. So my effective rate of interest here is going to be e to the interest rate, which is 0.06, and then I'm going to minus 1 from that. When I put that into my calculator, so this in calculator, I type the e with the caret, which is second law ln, and I put in, it prompts me with parentheses, I put in 0.06 and I just subtract 1 from it. This is no big deal about needing any extra parentheses. And when I did that, I got my effective rate of interest was 0.0618365, blah, blah, blah. But my screen ran out of room. So approximately my effective rate of interest written as a percent. So as a percent, this is 6.18. And let's round it 3 decimal places, so that 3 would turn into a 4, and put a percent on it. Which one's better? Well, and that will always be the case. Compounded continuously, they're putting more interest onto the interest, and so it's always going to be a little bit better of an effective interest rate. So instead of 6%, I'm really effectively getting, a little 6.2%. And same thing here, but this one's better. And I can see that because I took the decimals out so I could actually compare them better. So that's 6.7. We have one more section, 6.8 to do. And before I forget, I rolled a die. So for that last test we took on chapters 4 and 5, no, wait, is that right? Yeah. I rolled a die. And I rolled it for chapter 4, I decided, and I got a 5. So if you want extra credit, you can turn in the homework for section 4.5. And since this is Tuesday, it'll be due Thursday, 4:30, April 30th, at whatever your class start time is. So the deadline, if your class starts at 1:45, the deadline is 1:45. And if your class starts at 4:30, then the deadline is 4:30. So that's section 4.5 for extra credit for the homework. All right, so we're ready for 6.8. So let me get rid of this. So 6.8 is the more of a science type application of exponential ideas, whereas that interest stuff is more of a business representation of it. So 6.8 is all about this thing called the exponential law of growth and decay. Sometimes it's called the law of uninhibited growth or decay. And I wrote down the law, the exponential law of growth and decay, and oftentimes it's written real fancy, function notation, a of t equals a sub 0 e to the kt. Wow, what does all that mean? Well, notice to the right I wrote what everything stands for. See that a sub 0? That's the amount present at time equal to 0. In other words, it's the original amount. In other words, it's kind of like the present value. So a sub 0 is kind of like the present value. So this is kind of like the p. And then I said a of t, that's the amount present at any given time other than when, so in other words, what's my future value based on how much time has passed? That's what this guy is going to give me. So this is sort of like the a, or the future value, present value, future value. This was like the p, which is present value. T is time, and this time it's not restricted to years, it's just whatever the time is. If they're measuring it in days or years or hours, it doesn't matter. It can be whatever it is. So t is time. And the k, so there's the t, and the k is a constant. It's either going to be given or sometimes you have to solve for it, and I will tell you I like those problems the best. And the fact is if k is positive, then we're talking about exponential law of growth. And if k is negative, then we're talking about the exponential law of decay. In other words, if k is a positive and it's in the power, it's going to stay in the numerator and it's going to cause this to be e to it. It's going to grow exponentially. If k is negative, then that's e to a negative, which means it comes down as a denominator and we divide by it, and it's decaying. It's making everything smaller over here. And k, of course, is what's called the growth or decay rate. This is like the interest rate. This is sort of like the R. And that's like the time. So this looks like, which formula does this look like? It looks like the continuous compounding formula, right? That the A is equal to P e to the RT. It's exactly what it looks like. And it's the same sort of idea, except now we're doing it with things that are either growing or decaying exponentially, one way or the other. Two other definitions here are something called doubling time. Doubling time means, or is talking about the amount of time it takes for a quantity that grows exponentially, so it's getting bigger, to become twice its initial amount. We did that when we had that P go to 3 times its initial amount. That was tripling time. So doubling time is if you have an initial quantity, let's say that's 10, doubling time would be how long it takes it to get to 20. So double its size. Half-life, on the other hand, is the amount of time it takes for a quantity that decays, so it's getting smaller exponentially, to become half its initial amount. So if the initial amount is 10, half-life would be to find out how long it takes for that 10 to turn into a 5, where the future value would be 5. And we didn't do that with interest and money because the idea is we don't want our money to go backwards, we want it to grow. So this is half-life, where we're looking to see where our initial amount is cut in half its amount. So those two terms are important to understand what they're talking about. So I have 4 examples here, and then we'll be done with this section. And basically they're going to follow this law of growth and decay, or the law of uninhibited growth or decay. So if you see that word uninhibited, that's the same idea as exponential. So this very first example says, the number n of bacteria present in a culture at time t in hours, so we're letting t be hours, obeys the law of uninhibited growth. So that means it obeys the law of exponential growth. And they gave us the formula. They said that n of t, so real fancy, this is like my A originally in my other problems, is equal to 1,000 e to the 0.01 t. So this is future value, this is present value, e to the r, that's the rate, and that's the time, whatever the time is. So they've told me the formula that this follows, and now they've asked me some questions. So question A says, determine the number of bacteria at t equals 0 hours. We're going to do it formally, but think about this. T equals 0 hours. So right now, how much bacteria is there? It better be 1,000, because that's how this formula has been developed. This formula, this value right here, this a sub 0, that's how much is there right now when time is equal to 0. But let's go see if it works out. Basically what they're asking me to figure out is n of 0. So when time is 0, so I plug in 0 for time. 1,000 e to the 0.01 multiplying with time, which is 0. So n of 0, the amount present at time equal to 0, is equal to 1,000 multiplying with e to the power of what? 0.01 times 0 is 0. So n of 0 is equal to 1,000. I won't do that. So tell me about this right here. E is a constant, E is a number, and it's being raised to the power of 0, which turns it into what? A number to the power of 0 that isn't 0 is 1. So 1,000 times 1 is 1,000, exactly what we thought. When time is equal to 0, I didn't need to do all this. When time is equal to 0, the amount of bacteria is 1,000. So at time equal to 0, there are 1,000 bacteria. And I could have done that without doing all this work. It's just how the formula is set up. Part B says, what is the growth rate of the bacteria? Growth rate is, it's like the interest rate. The growth rate is 0.01. 0.01. It's growth because it's positive. If you want to, you can write that as a percent. So you could say, or it's 1%. So the growth rate is 1%. It's growing by 1%, more or less. So C says, what's the population after 4 hours? What's the population after 4 hours? Well, here's my formula, right? Now they want to know what's this future value when time is equal to 4. So in other words, we're trying to figure out n of 4 is equal to 1,000 times e to the 0.01 times 4. That's what I've got to go figure out here. Well, I can do this. I just have to put this into my calculator. So that means that my future value, which is what this n of 4 stands for, this is my future value, is equal to, if I put this in my calculator, I'm going to type in 1,000. I'm going to hit the second ln key and get e to a power of. And then how am I going to put this power in? I'm going to put 0.01 multiplying with 4, just one set of parentheses. This whole thing is the power, and so I'm going to do it like this so that I respect my order of operations. And when I do that and I put it in my calculator, it spit out 104.810774. There's more in the calculator, but that's as much as it could get on my screen. Let's round this to the nearest whole bacteria. We won't cut our bacteria in half. So bacteria, when time is equal to 4 at t equal to 4, which is what, hours, right? 4 hours is approximately 1,041 of them. We won't truncate it, we'll go ahead and round it. So after 4 hours, there's going to be about 1,041 bacteria in that culture. So it's showing us kind of how quickly it is multiplying or growing. Part D says, when will the number of bacteria reach 1,700? Maybe there's some study that says once it reaches 1,700, you're all doomed. But that seems to be the key number they want me to go figure out. When will it reach 1,700? So now, what have I been told about this equation? They want to know when, so we don't know the time this time, but what we do know is the future value. We want the future value to be 1,700. So my equation becomes 1,700 equals 1,000 e to the 0.01 t. I don't know what t is. How long will it take for the 1,000 bacteria to grow into 1,700? This is what I now need to solve. How do I solve this equation? Because I can't just plug things into my calculator yet, because here's where the unknown is. What kind of an equation is this? This is exponential, which means that I need to either try and create same bases, or if I can't create same bases, I'll put logs in front of both sides. Well, first of all, the base to this power is just e. It has nothing to do with the 1,000, so I need to get rid of the 1,000. How can I get rid of that 1,000? Divide it. So I'm going to divide both sides by 1,000. So on the left side, when I divide by 1,000, I get 1.7. The right side, I divide by 1,000, I get e to the 0.01 t. All right, so now I know what my exponential equation says. It says this. The base here is e. Can I turn 1.7 into a base of e? No way. So how do I solve this? I'm going to introduce logs in front of both sides. What kind of a log do I want to introduce? Do I want to do log base 10 in my calculator and use that key, or would it be more to my benefit to take an ln because it has a base of e. So again, if I see an e in my problem as a base, I will always take ln in front of each term instead of log. It'll make my life a lot easier. So I'm going to take ln of both sides. I'm going to take ln of 1.7 equals ln of e to the 0.01t. I absolutely want to see this line. I know sometimes in science classes when they do this, they just say if it looks like this, this is what you get, and they don't explain why. Okay, so here's the why to why that's happening. I want to see this line, absolutely want to see it in your work. And then I want to see this next line in your work, which says ln of 1.7 is equal to, so tell me about this. This is an understood base of e, right? So which property do we have going on here? I think that was property 2, where you have ln base e, and then the argument has a base of e, and these undo each other, and you are just left with 0.01t. I want to see both of those lines, okay? So I don't want you just to jump to the answer, which is usually, sometimes in science, they just go, oh, t is just going to be whatever the ln of 1.7 divided by 0.01 is, and you're like, well, why did that happen? And they just say, well, it just does. Well, here's why. We're solving an exponential equation using the process that we've learned. So how do I solve for t now? This is linear. So how do I solve for t? I just need to divide by 0.01, divide by 0.01, divide by 0.01. So t is equal to, I have to go put in my calculator, ln of 1.7 divided by 0.01. So when I put that into my calculator, again, in the calculator, I'm going to hit the ln key. It's going to come up with a parenthesis. I'm going to put in 1.7, and then I'm going to hit divided by, and then I'm going to type in 0.01. There's nothing here that I have to do other than that. There's only one term here, so we'll figure this term out, and divide them. And when I did that, what spit out was t is equal to, and I want to see this line as well. I want to know what your calculator spits out. So 53.06282511. It keeps going, but that's as much screen as I had, so that's as much as I could see. So that's what my calculator says t is. Now I will round it. So, and I will always tell you what to round to. I know I didn't on this handout, but I will on like a test or something. So I would like you to round this to 2 decimal places. So that means time is approximately going to be equal to 53.2 decimal places would be 0.06. And time is in what? Hours. So put your units on there. So it's going to take about 53 hours, or maybe closer to 54 hours, closer to 53 hours for this bacteria to increase to 1,700 from 1,000. One last question here. E wants to know, when will the number of bacteria double? I'll leave my formula there. When will the bacteria double? Part E. What does that mean? They're asking me for doubling time. When will the bacteria double? It starts at 1,000. So they want to know how long will it take for it to get to 2,000. When will it double? So my equation is 2,000 future value equals 1,000 present value e to the 0.01t. How long will it take for that to happen? Well, it better be more than 53 hours, or else I'm doing something wrong, because this was 1,700. Now I want it to get up to 2,000. Same process though. So this is exponential. I need to get rid of the 1,000, so I will divide both sides by 1,000, and look what's over there. 2 equals e to the 0.01t. And I know sometimes in science class they just go, well, if it's doubling, then there's going to be a 2 over here. Well, this is why. So it's following this equation. I divide both sides by 1,000. I get 2 equals e to the 0.01t. This is exponential. I cannot create same basis, so I'm going to introduce a log. What log will I introduce in front of both of the terms? ln, because it will make life easier for me. So I want to see this line. ln of 2 equals ln of e to the 0.01t. I want to see that line in your work. And then I'm going to solve this, and this says ln of 2 equals what does this all simplify into? Rule property number 2 says ln base e of a base of e in the argument to that power just leaves me with 0.01t here. Or again, if you want to use that other property that says you bring this out as a multiplier, 0.01t times ln of e. So alternatively, 0.01t times ln of e, but ln of e is equal to 1, and 0.01t times 1 would give you 0.01t. Either way you look at it, you get it to here. I want to see that line. I want to see these. I want to see them happen. And now what kind of an equation do I have? This is linear. All I have to do is divide by 0.01, divide by 0.01. So when I put ln of 2 divided by 0.01 into my calculator, my calculator spit out 69.31471806. That's as far as my screen went. So let's round this to the nearest, to 1 decimal place, nearest 10. So time is approximately equal to 69.3, and this is hours again, which looks pretty good. It needed to be bigger than this clearly, so I feel pretty good about those answers. So solving these exponential law of growth and or decay problems, let's go and take a look at number 2 and see what we can do with it. So these are kind of fun, huh? Hear that, but someone's having fun outside going down my street on their noisy motorcycle. So number 2 says iodine 131 is a radioactive material that decays according to the exponential law of decay, and they actually gave me the function. They said it decays according to A of t is equal to a sub 0 e to the negative 0.087t, where t is in days, so this time is being expressed in days. And notice it's negative, which means it's decaying, it's getting smaller each time. And the original sample of iodine 131 is 100 grams. So what have they just told me in this formula? They just told me that at time equal to 0, they told me the present value, right? Which is 100. So I'm going to put in 100 e to the negative 0.087t. So they gave me a little piece of information there that I can take advantage of. They told me what the initial amount is at time equal to 0, 100 grams. So part A says, so here's the formula I'm going to be using. Future value equals present value, which is 100, times e to the, and they told me the k, negative 0.087t. So part A says, what's the decay rate? Okay, well the decay rate is negative 0.087. Or if you want to write that as a percent, it would be negative 8.7%. In other words, it's decaying by negative 8.7% per day, since this is the time is in days. Part B says how much iodine 131 is left after 9 days. So they're telling me the time and they want to know the future value, how much is left after 9 days. So in other words, A of 9, if I write it fancy, is equal to 100 e to the negative 0.087 multiplying with 9 is what I have to go figure out. So in my calculator, very carefully, again, I'm going to type 100 e, caret comes up, parenthesis comes up, and I'm going to type negative 0.087 times 9, all in one big set of parentheses. Don't set, I know I have it separated out here, but I have to understand the calculator. I want it to figure out that product, and that is my power. So when I do that, what spits out for me was 45.703284. It keeps going. Let's round this to 1 decimal point. So that means that the amount of this iodine 131, so amount of iodine 131 after 9 days is approximately 45.7, and this is grams? Yeah, grams. So after 9 days, the amount left is approximately 45.7 grams. Does that make sense? Remember we said it's decaying. It started at 100. Awesome, it's down to 45.7 grams after 9 days. That's good. It's decaying. It's getting smaller, which is what should be happening if I'm figuring things out correctly. So next question says, part C, when will 70 grams of iodine 131 be left? So when will 70 be left? So it should be less than 9 days because clearly we're not taking as much of it away here. So how long will it take for 70 grams to be left? So in other words, my future value, I want to be 70 equals 100 e to the negative 0.087 t. So I don't know how long, that's what I'm trying to figure out. How many days will there only be 70 left? Well, again, this is like the one that we did before, where this is exponential. The unknown is in the exponent. I want to try and create same bases. The base here is e. The 100 has nothing to do with this base and power, so I'm going to divide away the 100 so that I can look and see what I have going on here. So this is 0.7 equals e to the negative 0.087 t. Exponential, can I make same bases? No way. So I'm going to take ln in front of both of them since I see an e. So here's the line I want to see. ln of 0.7 equals ln of e to the negative 0.87t, 0.087t. I want to see that line, and then I want to see the next line, which says ln of 0.7 is equal to, this simplifies into just negative 0.087t. It's not linear, so all I need to do, so I want to see those two lines, is divide by negative 0.087. Negative 0.087. So when I take ln of 0.7 and I divided it, where is it, by negative 0.087, so when I did this, my calculator spit out 4.0997119999. There's more to it, but that's as far as it went. Be very careful here that's use the negative key, not the minus key, because otherwise it will give you an error message. So that means that, how long will it take? Let's round this to 1 decimal place. So time is going to be approximately 4.1, and time was being measured in days. So it's going to take about 4.1 days for it to go down to 70, which makes pretty good sense since that was 9 days. It went down to 45.7. And we have one more question here, part D. Let's go take a look at that one. Over here. So D says, what's the half-life of iodine 131? So what are they asking for here? What did we start with? We started with 100 grams, right? So half-life, that means they want the 100 grams. They want to know how long it takes the 100 grams to turn into how many grams? Half of 100, so 50. So this equation is going to be 50 equals the 100 e to the power of negative 0.087 t. In other words, how long does it take for the 100 to turn into 50? That's what we're trying to figure out here. So the half-life. Again, it's exponential. The 100 has nothing to do with the power, so I'm going to divide it out so I can see exactly what the base is here. So when I divide 50 over 100, guess what I get? Half. 0.5. Remember doubling time? I got a 2 over there. Half-life, I get a half, or a 0.5 over here. This is why it's happening. So I want to see that. I want to see that you understand what's going on as opposed to just being told, well, that's what will be over there. So this turns into e to the negative 0.087t. So 0.5 equals this. This is exponential. I cannot create same bases. I can't turn 0.5 into a base of e or vice versa. So I'll introduce an ln in front of both because of that e. So ln of 0.5 is equal to ln of e to the negative 0.087t. Again, I'm going to stop putting the little asterisks here. I want to see these lines. Then I simplify this. Ln of 0.5 is equal to, this just turns into negative 0.087t. And now it is linear, so I'm going to divide both sides by negative 0.087, divide by negative 0.087. So t is equal to, I take that ln of 0.5 and I divide it by negative 0.087 in my calculator, and my calculator spits out 7.967208.972, blah, blah, blah. I can't see anymore on my screen. So let's round this one to 2 decimal places, so to the hundredths place. So this is 7.97, and again, this is days. So it's going to take almost 8 days for it to be half as much as it used to be. So its half-life is almost 8 days, 7.97 days. So we have 2 more problems to do here. So let's flip over and take a look at number 3. So 3 says a culture of bacteria obeys the law of uninhibited growth. So that automatically means it's obeying the A of t is equal to A sub 0 e to the kt. It's obeying that law where this is the present value, future value, rate, and time. And it says, part A, if n is the number of bacteria, so they don't want me to write a's here, they want me to write n's. If n is the number of bacteria in the culture, and t is the time in hours, express n as a function of t, for goodness sakes. So n of t is equal to n sub 0 e to the kt. So they just want me to use n's instead of those a's. Doesn't really matter. They're just being picky here. I think they probably have one like this in the homework, and I wanted to make sure you understood what they were asking for. Part B says, if 500 bacteria are present initially, so what have they just told me? They've told me the present value, right? So I'm going to adjust this formula now that says n of t is equal to, they've told me 500 are present initially, so this is now what the formula looks like. N of t equals 500 e to the kt right away. They've given me a piece of information which is very useful. And then it says, and there are 800 after 1 hour. So they're telling me when t is 1, there's going to be 800 here. Interesting. Then they say how many will be present in the culture after 5 hours. What have they never told me? Nobody's ever told me the k, right? And that's the type of, this is the type of problem now where they haven't told me that growth rate or decay rate, and I'm going to have to go figure it out based on the information they've given me. So here's the first piece of information they gave me, and then what did they tell me? They said when t is 1, the future value is 800. So they observed this bacteria for an hour, and they counted them. And after an hour, there were 800 bacteria. So that means my future value is 800. We start at 500, and in 1 hour, when t is 1, this 500 turns into an 800. So that's what that piece of information is telling me. When time is 1 hour, the original amount ends up being 800. Guess what this is going to help me to do? This is going to help me solve for k. In other words, they gave me all the pieces of information except for the k, so now I'm going to go solve for k. So let's go see if I can do this. First of all, this says 800 equals 500 e to the k times 1, which is just k, right? What kind of an equation is this? Well, it's exponential again. So again, this 500 is not part of that exponent, so I'm going to divide it away so I can see what I have going on for my bases. And this is 1.6 equals e to the k. All right, it's exponential. My base here is e. The base here is 1.6. There's no way I can create same bases. So since I see an e, I'm going to take ln of both sides. Again, this is the line I want to see, ln of e to the k. And then I want to see this line, ln of 1.6 is equal to, what does this simplify into? This simplifies into plain old k. Guess what? There's k. Do not put this in your calculator and give me an approximation of it. Do not do that. Understand this k is part of this formula, and if you already round it here, then you're going to have all sorts of problems using a rounded answer within a calculation of a problem. So this is k. Do not approximate. Do not approximate this. We only approximate final answers, not pieces that are inside the formulas that we're then going to calculate. You're approximating too soon. You're rounding too soon. All right, so that's k. I'm not done with this question. That's just using the piece of information that in 1 hour, the future value will be 800. But what this does for me is this. It now tells me, so now my formula is n of t, future value is equal to present value, which is 500, e to the k, which is ln of 1.6 times t. And honestly, keep in mind, see k times t? K times t is multiplication. I can do it in any order I want to. If k is an awkward answer like this with a log, then I would rather put the t multiplying first. So I'm going to write t times the ln of 1.6 because it'll be easier for me to deal with in the formula. So this is what my formula now says. I have all the pieces I need. I have the k, the rate of growth, and I have the initial amount. And now I can figure out anything they want me to do. So the rest of this question for part B is, how many will be present in the culture after 5 hours? And so what are they asking me for? They've told me time, right? So they're asking me to figure out n of 5. So I'm just going to plug in 5 where the t is. So this is 5 times the ln of 1.6. So I just need to put this in my calculator, so that's not too bad. So n of 5 is equal to 500e to the 5 times the ln of 1.6 in my calculator. In calculator, I type in 500. I hit the E key with the caret comes up. It puts a parenthesis asking me to put the power in. And the way I type in the power is like this. 5, you don't even need to put a times sign there. Hit the ln key, parenthesis comes up, put in 1.6, close that parenthesis, and then close the parenthesis that came up for the power. So be careful with the parentheses. You have to have the same amount of left parentheses as you do right parentheses, or else it's going to tell you have an error in your calculator. And when I put that into my calculator, it spit out 5242.88. Actually, it spit out kind of something that didn't need to, it doesn't keep going, it actually terminates. So what does this mean? This means that after 5 hours, there is 5,242, well, let's round it to the nearest whole bacteria. There is approximately 5,243 bacteria if I round it to the nearest whole bacteria. So after 5 hours, 5,243 bacteria. Well, that's multiplying pretty quickly. It went from 500 to 5,000 in 5 hours. Lots of fives there. So part C says, let's get rid of this. C. So C says, how long is it until there are 20,000 bacteria? So this time I don't know time, right? But they're telling me that my future value needs to be 20,000. So how long will it take for there to be 20,000? So this is 20,000 equals 500 e to the t times the ln of 1.6. That's what I have to go figure out. So 20,000 equals 500 e to the t times the ln of 1.6. Well, again, this is exponential. There's my unknown up there in the power. the e is part of the power of the 500 isn't, so I'm going to divide away the 500, divide away the 500, so this gives me 40 equals e to the t ln of 1.6. So now I need to think about same basis, but there's no way I can turn 40 into a base of e or vice versa, so I'm going to introduce an ln in front of both. Here's the line I want to see, e to the t ln of 1.6. I'm going to simplify. Here's the other line I want to see. ln of base e of e to this power just leaves me with the power, which is t ln of 1.6. This is linear. How do I solve it? I divide by ln of 1.6. Divide by ln of 1.6. Look at that. T is going to be this division of ln of 40 divided by ln of 1.6. And when I do that, there shouldn't be anything tricky about this in the calculator. You're just going to type in, so in calculator, you're going to type in ln, parenthesis comes up, close it, divided by, type in ln, parenthesis comes up, close it. It's just one term over one term, so there's nothing complicated in terms of putting that into your calculator. And so when I did that, I got t was equal to, and again, I want to see what your calculator spits out, and then you can round it for me. 7.848619084, keeps going, but the screen ends. So let's round that in time to 2 decimal places. So this is approximately 7.85, and what was time? It was hours, right? Oh boy. So in about 7.85 hours, this bacteria is going to go from 500 to 20,000. I think I need to go to the ER. It's not going to take very long for that to happen. That's like 7 hours and maybe 50 or 51 minutes or something. It's not going to slightly less than 8 hours. I'm in trouble. So we have one more problem here to look at, number 4. Interesting that we're talking about problems like this with the issues that we're dealing with now. Trying to stay healthy. I hope everyone is staying healthy, getting used to wearing those masks when we go outside. So number 4 says the half-life of a radioactive substance is 6 years. If 10 grams is present right now, how much will be present in 11 years? Well, the fact that they're talking about half-life in a radioactive substance means that they're implying that this follows the exponential law of either growth or decay. The fact that they're talking about half-life makes me think it's of decay. So I need to have a formula here so that I can follow. So let me think about this. If it follows that exponential law of decay, we're talking about a of t is equal to a sub 0 e to the kt, where this is the future value, this is the present value, that's the rate of decay, and that's time. So let me see what I can fill in here. It says the half-life of a radioactive substance is 6 years. Okay, I'm going to hold on to that for a moment. If 10 grams are present now, so 10 grams, where does that go? That's this a sub 0. So now my formula looks like this. A of t equals 10 e to the kt. So 10 grams are present right now. How much will be present in 11 years? That's something future as well, because that's saying what would this number be when t is 11, but I don't know what k is yet. So I need to go figure out k. They haven't told me the decay rate, but they've told me a way to figure it out. And it's that very first sentence. It says the half-life of a radioactive substance is 6 years. They've told me how much will be present in 6 years. So let's go fill that in and we'll be able to figure out the k. So how much is going to be present in 6 years? They said it the half-life. Half-life is 6 years. So when t is 6, half of this will be left. So my future value in 6 years is going to be 5. And t is 6. So in 6 years, this 10 will be 5. So they've given me everything I need to know to go figure out my k, and then I can go answer the rest of this question. So I need to solve this. This says 5 equals 10 e to the, let me write this nicer, 6k. I'm trying to solve for k, it's exponential. So that means I need to create same bases. The base here is e, I need to get rid of the 10. So I'll divide the 10, divide the 10. Oh, there it is, half, right? So 1/2, or it's easier just to use a decimal, so I'll write down 0.5 equals e to the 6k. So how do I solve for k now? It's still exponential. Cannot create same bases, so I will take ln of both sides. Here's the step I want to see. ln of 0.5 equals ln of e to the 6k. One more shot here, a step I want to see. ln of 0.5 equals, this simplifies into 6k. This is now linear, so I divide both sides by 6. So I get k is equal to ln of 0.5 divided by 6. Do not put that in your calculator. Do not give me a decimal approximation of that. This is something that's going to go into this formula that I need to leave just the way it is. Don't round it, because you don't want to use rounded numbers in a formula that you're now calculating with other numbers. That's rounding in the middle of a problem. No good can come from it. So I can tell you that many, many years ago, in the NASA program, so maybe back in the 50s or 60s, they were calculating an orbit of something, a satellite or something, and one of the scientists who should have known better rounded in the middle of the problem. And that satellite went millions of miles off course because of it, because they were talking very, very large numbers. They rounded in the middle of a calculation, and so they were many, many miles off of what the course actually was, and the thing blew up because it didn't go where they were expecting it to go. And I assure you that NASA scientist probably lost his job, which is not nice, but anyway, don't round in the middle of a problem. So this is k. K is ln of 0.5 over 6. So that means that my formula now says a of t is equal to 10, the initial amount, times e to the kt. But again, t is usually easier at this point to put in the front, multiplying with the k, which is ln of 0.5 over 6. So t times ln of 0.5, and then divide that by 6, because t is like t over 1. So this is basically just t ln of 0.5 all divided by 6. So there's my new formula now. So a of t is equal to 10 e to the t times ln of 0.5 all over 6. So what do they want me to figure out now? So the last piece of the second sentence says, if 10 grams is present now, which we have right there, how much will be present in 11 years? So in other words, they want me to figure out the future value when time is equal to 11 years. And let me see here again. They said the half-life was 6 years, right? So I better get something less than 5 or else I'm doing something wrong. So let's go see what happens here. I need to figure out a of 11. So I've got 10e times 11 to the power of 11 times ln of 0.5 over 6. That's what I've got to go figure out. So I put that very carefully into my calculator. So in calculator, I'm going to type in a 10 and e. It brings up the power and a parenthesis. And then I'm going to type in 11 ln 0.5. And again, when you type in the ln, it brings up a parenthesis. So close it to show the argument. 11 can be right next to the ln. That's an understood multiplication. And then I'm going to divide by 6 and then close the parenthesis of that power. So again, this respects order of operations. It's going to take 11, multiply it with the ln of 0.5, and then divide that answer by 6, which is exactly what this is saying. T times this is just t on the top and the 6 on the bottom. So this looks good, and when I put that into my calculator, a of 11 is equal to, it spits out 2.806155121, which, let's do this to 2 decimal places, to the nearest hundredth. So that means after 11 years, what will be, so how much is present? Approximately 2.81 grams of this radioactive substance are present. So that's good. We said 5 would be present after 6 years. After 11 years, almost twice as much, 2.81 grams are present. So this one is decaying nicely, which is good. Some radioactive substances don't decay quite so nicely. So guess what? We just finished chapter 6. All that's left is chapter 7, and again, chapter 7 is just 7.2, 7.3, and 7.4. 7.2 is learning how to graph sideways parabolas, and 7.3 and 7.4 is learning how to graph ellipses and hyperbolas, which we will do all of that on Thursday. And again, I think if you recall, somewhere along the line during this lecture, I gave you an extra credit opportunity. Let's see, and if you're watching this early, because I usually send this out on Monday, don't forget you have a quiz due today, Tuesday the 28th, at the beginning of your class time, no later. Remember, a minute late is -5 points, and another minute late, 2 minutes late, is -10 points, and the quiz is only worth 10 points. So make sure you get it turned into me on time. And I think that's all I've got to say. I will see you all on Thursday to have a little fun graphing what's called conic sections. So see you later. Have a good Tuesday night.